Welcome to this week 6 video. On this video, we're going to talk about uh, the importance on simulation and verification in CAM. This is intended for design engineers, manufacturing engineers, architects to know about the benefits of simulation and verification. We're going to start with a little introduction of this topic. We're going to start talking uh, about the principles and practices of CAM simulation and verification. Um, to start with the verification principles, what we have will be first that when we have the software, we need to find the collision detection. Collision detection is crucial for CAM simulation and verification, ensuring that the cutting tool, the workpiece, the fixture, and machine components do not collide during the machining process. It's important to identify and address potential collisions before actual production helps prevent costly mistakes and machine downtime. Collision detection in CAM involves analyzing the interactions between different elements of the machining process, such as the cutting tool, the workpiece, the fixtures, and the machine components. The primary goal of collision detection is to identify any potential collision or interference that may occur during the machining process and to resolve the collision before the actual production begins. This process helps minimize the risk of costly mistakes, machine damage, and production delays. The geometric analysis of the element that we're going to fabricate, it's important that we know that the element that we're cutting fits on our machine, so we don't have any issue with the size of the plate or the element that we're placing. Well, this involves examining the geometries of the cutting tool, the workpiece, the fixture, and machine components to identify potential points of contact or interference. Geometric analysis takes into account the dimensions, shapes, and relative positions of these elements throughout the machining process. The kinematic analysis uh, focuses on the motion and dynamics of the machining process, how the machine will perform to make the cut that we need. This includes the movement of the cutting tool, the workpiece, and machine components. By analyzing the motion of these elements, potential collisions can be identified and addressed throughout adjustments to the toolpath or machine configuration. And simulation plays a critical role on collision detection. We can provide a virtual representation of the machining process, and this enables the user to visualize the interactions between the cutting tool, workpiece, the fixtures, and machine components. This makes it easier to identify potential collisions and make necessary adjustments. By detecting and resolving these potential collisions, it's essential to address them before the production begins. Because once you already send the order to fabricate and this is not correctly done, you can damage the machine or you can waste material. You need to adjust the toolpath, modify the workpiece, or fixture design. In some cases, it may also be necessary to update the machining parameters, such as the feed rate, the spindle speed, to ensure safe and efficient operation. Like this picture, we see different options on cutting on different axes. to get the element. So we have the different forces that will be needed to fabricate that special shape. We may also need to analyze the material removal, the amount of material that we're going to remove when we cut this tool. We can simulate the material removal process in a CAM software to verify that the toolpath and machining parameters will result on the desired part geometry. This analysis helps to identify the areas of excessive or insufficient material removal and enables adjustments to be made before the actual machining begins. We also have to consider that sometimes this material needs to be stored on a special place, and maybe you can recycle the material, or if you don't have how to recycle it, you will have to place it on a waste disposal. And to do that, you need some type of volume, specific volume, according to the analysis, to put that waste on the disposal. Well, the virtual representation of the material removal relies on the virtual representation of the workpiece within the CAM software. This digital model enables the user to visualize the effects of the planned machining operation on the workpiece and assess whether the desired geometry and tolerances will be achieved. Well, we already seen this on the previous video, the toolpath evaluation. This analysis involves evaluating the toolpath generated by the CAM software to ensure that the result in the desired material removal. This includes assessing the tool engagement, the cutting depth of the cutting tool, the step overs, and the feed rates, and this will help to optimize the material removal and minimize the risks of the tool to break or excessive tool wear. We also need to assess the machining parameters. This is important parameter to address for material removal. This involves analyzing the spindle speed, the feed rate on the machine, the cutting depth, to ensure that this is suitable for the material being machined and the desired part geometry. We need to do adjustments to these parameters to optimize the material removal and prevent any issues such as chatter, excessive tool wear, or poor surface finish. Depending on the machine that you have, you need to configure the parameters each time you're going to cut. And well, if the material removal analysis identify different areas where you have excessive or insufficient material removal, it's important to address these issues before the actual machining begins. This may involve adjusting the toolpath, changing the machine parameters, again, modifying the cutting tool geometry to achieve the desired material removal and part geometry. As you can see, all these steps are important and are related because once you approve the machine to cut, there will be no way back, and sometimes if you don't follow these steps correctly, you will lose the material and waste time, and the production will be affected. And that's why the verification is the most important step when you're working with this type of machines. Once the adjustments have been made based on the material removal analysis, the simulation should be rerun to verify that the changes have effectively addressed the identified issues. This iterative process helps to ensure that the final toolpath and machining parameters are optimized. This is meant for efficient material removal and high quality part production. What we're seeing on this picture, it's this software called Cabinet Vision, where you can program different furniture parts and program this to the CNC, verify the measurements, verify the sizes of the different parts, and program also what type of tool you're going to use and see the tool path also. So verification is always important to have the best product on the final process. Well, and according to the use of the machine, we can also estimate the tool wear. Estimating tool wear during simulation and verification helps to predict the lifespan of the cutting tool and plan for tool placement. Understanding the tool wear pattern can also inform adjustments of the tool path or setting the cutting parameters to extend the tool life and optimize the machining efficiency. These tools are not forever, so you need to always adjust the better parameters to make this work. And if the tool has been used many times, you will need to change another cutting tool. And to analyze the key aspects of tool wear estimation, we have the tool wear models. It is possible to generate a tool wear model that typically relies on mathematical models that consider factors such as the cutting speed, the feed rate, the depth cut, material properties, and the cutting tool geometry. These models can predict the tool wear progression based on the machining parameters and the tool paths being used. This will help to estimate the remaining tool life of the cutting tool that we're using. Well, and monitoring cutting forces, it's also important for the machine and the tool. Cutting forces can be significant and have a significant impact on the tool wear. And by simulating the cutting forces during the machine process, users can identify areas where excessive forces may lead to accelerated tool wear or the tool to break. Adjustments to tool paths or cutting parameters can be made to minimize these forces and prolong the tool life. Also, in some advanced CAM software, tool wear simulation can be integrated into the overall machining simulation. This allows users to visualize the wear progression on the cutting tool throughout the machining process and identify areas where adjustments may be needed to extend the tool life or maintain the part quality. On this example, we're seeing, well, this is not part of a CAM software, but this is a simulation on where the force is applied to cut certain type of material and the wear generated on the cutting tool. You can see this by different color gradings and analyze what is the impact of the tool and maybe see what will be the tool life, expected tool life that you're going to have. We may also have some adaptive machining strategies. Some CAM software systems offer these adaptive machining strategies that automatically adjust the tool paths and cutting patterns based on predicted tool wear. These strategies can help optimize the tool life and machining efficiency by ensuring that the cutting tools are used within their optimal performance and range. On this picture, we can see how this part is being cut, and you can configure the software to program the tool path on the best way according to the cutting tool that you're going to use. And well, another important aspect of to maintain the tool in the best to have the best performance will be to see the tool life management. By understanding and predicting the tool wear, manufacturers can implement a more effective tool life management strategies. This may include scheduling regular tool replacements or incorporating tool monitoring systems to track tool wear in real time. This will enable proactive tool changes and minimize the machine downtime. We may also have the surface finish prediction with the CAM simulations. We can use this to predict the surface finish of the final part based on the chosen toolpaths and tools. This information will help determine whether the desired surface finish will be achieved and inform any necessary adjustments to the process. Other analysis that we may have will be the surface roughness models. The surface finish prediction typically relies on mathematical models that consider factors such as the tool geometry, the feed rate, the cutting speed, and the depth cut and material properties. And these models can estimate the resulting surface roughness based on the machining parameters and tool paths being used. The way we set up the tool path, it's also important and have a significant impact on the surface finish of the final part. For example, a constant step over scallop height or constant scallop tool paths can be chosen based on the desired surface finish requirements. The CAM software can help users to compare different toolpath strategies and select the most appropriate one for their specific surface finish goals. As you can see, depending on the shape, well, this picture is showing different toolpaths for different shapes. On this side, we have a morphed spiral toolpath. On the right, we have a radial toolpath to follow with a completely different shape. On the lower left side, we have the adaptive clearing with a concave shape. And on the right, we have a pocket toolpath with a sphere and some grading on the surface. The toolpath selection is also an important part of all this process. The choice of the cutting tools, such as end mills, ball nose mills, base mills, plays a vital role in achieving the desired surface finish. And CAM software can help users to identify the most suitable tool for their application and evaluate how different tool geometries and materials will affect the surface finish. there are different types of tools for different shapes and different applications. The machining parameters optimization also involves adjusting the machining parameters such as the feed rate, the cutting speed, the depth of cut, and this can help improve surface finish. The CAM software can assist users in finding the optimal balance between productivity and surface finish by simulating the impact of different parameter combinations on the final part. Well, and sometimes some advanced CAM software systems can provide simulation and visualization tools that allow users to see the predicted surface finish on a virtual part model. This visual representation helps users identify areas where adjustments may be needed to address the surface finish requirements. What we're seeing is what is the toolpath and a simulation of how the machine will cut a certain type of piece and how it will perform the work. Well, now we're going to see this video about G-code driven machining simulation in NXCAM. Well, this Siemens NXCAM is known for part fabrication, and we're going to see how we can do a simulation on this software.
In this video, NXCAM's integrated simulation and verification module, known as ISNV, is shown. This product is a fully integrated machine tool simulation. Run the digital twin to check post-processed machine code before sending them to the machine tools on the shop floor to ensure a safe and optimized collision-free NC code. The system will recognize possible collisions of all involved components, as well as the material removal in-process workpiece, and check for excess travel limits to ensure the setup fits to the machine tool configuration. The Virtual Driver Core is a powerful Common Simulation Engine, or CSE, which is fully configurable to almost any machine controller characteristic to cover multi-channel mill-turn machines as well as NC code-driven robots. On top of that, the system offers support to optimized NC code, for example, a detailed time analyze to fine-tune the machining time. Let's make that clearer. Almost any CAM system offers an integrated simulation based on the internal toolpath representation, but not on the post-processed NC code. Internal toolpath simulation is sufficient as a first pre-check. However, the more complex the machine tool becomes, the more specific controller features are used. The simulation of the post-processed machine code is essential to ensure a safe machining process. Simulate post-processed NC code can be done using third-party software products, which will increase cost for license, training, as well the data transition between the systems could be challenging. All of which is not needed with NXCAM, as it offers a fully integrated machine code-based simulation, all in NXCAM. A special solution, the high-end virtual machine, includes a software from the real controller, for example the Xenomeric VNCK, and comes together with the exact machine tool configuration provided by the machine tool vendor. Let's see a typical use case. Start with the NXCAM, in this case an impeller. First, I would like to add the machine tool from the library. Let me pick a Hercules C42 for that case, a typical 5-axis machine equipped with a Xenomeric controller. At any time during programming, the user can select any operation, switch to the simulation environment, the ribbon changed, showing all simulation features and controls. The post-processed NC code will be shown in the execution view, and by press play, start the simulation. The accuracy and precision of any system is based on the underlying data like the kinematics model and the motion planning of the dynamic axis properties like D and S acceleration, dragging and more. These will be defined once per machine tool with the Machine Tool Builder application of NXCAM product suite. Ensure matching the data precise to the real machine tool with the underlying virtual twin of the controller model. A high close to reality simulation is guaranteed. Another typical use case, is the need to simulate existing NC code, as in some cases you may not have the fully programmed CAM example, or for mass production you are modifying your NC code before sending it to the shop floor. That can easily be achieved by dragging and dropping the NC code file into the program manager, where it will be possible to edit the NC code. All used main subprograms or any used machine cycle are handled in the program manager, including integrated editor features. Monitoring NC status like feeds, speeds, loaded tool or active offset and more, analyze and debugging features like watch the NC variables will be displayed during simulation. Breakpoints can be set easily to any NC code line to stop the simulation. The overall machining time will constantly be updated and is always visible in the ribbon. Available as an extra feature are the machining times in detailed breakdown of primary and secondary times, as well as cutting and non-cutting time. That can be used for a detailed analysis to further optimize the NC code, especially used in mass production. This is accomplished by the highly sophisticated motion planning of the controller driver capability, and remember, all fully integrated into NX. Important to the content in regards to the machine tool model, post-processor and simulation libraries. With the installation of NX, you get multiple different machine tool kits from 3 to 5 axis milling, as well as complex multi-channel mill turn centers with the most commonly used controller models all out of the box. There's examples that show how those can be used directly in the resource bar of NX CAM. On top of that, Siemens offers a web-based platform, PostHub, which allows you to search for more post and machine toolkits. The concept of post and driver is open and can be customized to any specific machine tool controller characteristic. To summarize what was shown, the high-end capability of the total integrated simulation in NX CAM. We saw how machine code-based simulation using the post-processed NC code can check for collision and access limits violation to ensure a safe process before sending the data to the shop floor. We saw details of external NC code simulation, edit and time analyze to optimize the NC code, as well as what comes with the out-of-the-box installation. We saw how simulating exactly what sent to the machine tool ensures a close-to-reality simulation, all integrated into NX. The Integrated Simulation and Verification Package, ISV, is available in most NX CAM bundles or available as add-ons. Thank you for watching.
Well, running simulations on a CAM software, to perform this CAM simulation and verification, the toolpaths, machining parameters, and others must be loaded into the CAM software. This software will then simulate the machining process, allowing the user to visualize the material removal, the tool movements, and potential collisions. This is the first step for running a simulation. This is to load the generated toolpaths and the associated machining parameters. This will be loaded into the CAM software, and this information forms the basis of simulation and directly impacts the accuracy of the results. In order to prepare the machine, we need also to set up the fixtures of the machine if we have any clamps or any other fixture that we can use. This is intended to ensure the accurate simulation. The machine and fixture setup should also be defined within the CAM software. This includes specifying the work coordinate system, the machine kinematics, and any clamp or fixture that will be used during the machining process. Accurate machine and fixture setups will help prevent collisions and ensure the proper alignment during the simulation. And there are different materials that we may use and different machines for different materials. So the material definition, it's an important aspect also. Defining the material properties of the workpiece is essential for running a simulation. The material properties such as density, thermal expansion, and cutting forces can affect the machine process and should be accurately represented in the simulation for reliable results. Well, the material definition is also crucial when you want to purchase a machine. For example, if you're going to cut wood, you will have certain type of wood, a wood machine, and a difference that if you're going to cut maybe a metal sheet, you will have a different type of machine and also another kind tool. So this will also involve that you will need a space. You will be needing electrical source to energize the machine. And depending on the machine that you select, you need other type of accessories. The simulation environment within the CAN software allow users to visualize the machining process in a virtual environment. This includes the display on the workpiece, the cutting tool, the machine components and fixtures. The user can observe the tool movements, the material removal, and potential collisions in real time or step through the simulation in a controlled place. Here's where we need to identify the issues and make the adjustments. During the simulation, users can identify issues and collisions for excessive material removal, poor surface finish, or inefficient tool paths. Based on the simulation results, users can make the adjustments to the tool paths, machine parameters, or setup to address these issues before the actual machining begins. This will be resolved into an iterative process. Running simulations in the CAM software, it's an iterative process, and users may need to perform multiple simulations, make different adjustments, and re-evaluate the results until they achieve the desired outcome. This iterative approach helps to ensure that the final machining process is efficient, accurate, and free of potential problems. And by analyzing the simulation results, after running the simulation, the user must be careful by analyze the results, check for any potential issues such as collisions, excessive material removal, insufficient material removal, or poor surface finish. If any issues are identified, adjustments to the tool path, to the tool, or the machining parameters should be made before the actual machining process begins. When we talk about collision detection, you need to carefully review the simulation results to identify any potential collisions between the cutting tool, the workpiece, the fixtures, or any machine component. These collisions can lead to machine damage. Sometimes this machine damage or any scraped parts or safety hazards may involve time lost, and it is a big cost to fix this type of machines. So that's why it's crucial to address this before the machining begins. You don't want any accident during the machining process. You don't want any material being damaged, and also you don't want to damage the machine itself. When you also analyze the material removal patterns and compare them to the desired part geometry, you will identify the areas of excessive or insufficient material removal and adjust the tool path or machining parameters to correct these issues. Ensuring the proper material removal helps achieve the desired part geometry and reduces the need of additional finishing operations. And the surface finish evaluation will involve to examine the predicted surface finish of the machine part in the simulation results. If the surface finish does not meet the desired specs, the adjustments to the toolpath, the tools or machine parameters may be necessary. Achieving the desired surface finish in the machining process can help minimize the post-processing and improve the part quality. All the importance of the tool wear estimation. When we review the tool wear predictions in the simulation results, this to determine if the cutting tools will last for the entire machining process or if the tool replacement will be required. The adjustments on the tool path or machine parameters can help optimize the tool life and reduce the frequency of tool changes. This will improve the overall efficiency. In this picture, we can see a microscopic view of the tool on the tip, and we can see the corner wear and the flank wear of the tool. And well, we can, by analyzing this wear on this tool, we can see if we need to change the material, the tool that we're using, or we can keep it. This is normally used when you have 15 minutes of use, and on the right we can see when we've been using the tool by 30 minutes. The limit, as we can see on the lower table, the maximum tool wear will be on this spot here. The cycle time analysis, it's about to analyze the predicted cycle time of the machine process based on the simulation results, and if the cycle time is longer than desired, adjustments to the tool paths or machine parameters may be necessary to optimize production efficiency. And as I mentioned, this is an iterative process. We have to analyze the simulation results, make adjustments, and repeat. Users may need to perform multiple simulations and analyze the results, making adjustments as needed until they achieve the desired outcome. This iterative approach helps to ensure that the final machining process is efficient, accurate, and free of potential problems. And while this CAM simulation, it's an iterative process. This often requires multiple rounds of adjustments and simulations to achieve the desired results. Each iteration should bring the process closer to an optimized, efficient, and error-free machining plan. We can start with an initial simulation to run the first simulation using the initially created toolpath and machining parameters. And here's where we're going to analyze the results to identify any potential issues, the collisions, excessive material removal, or maybe insufficient material removal. Also, the poor surface finish or excessive tool wear. Then we need to make adjustments based on the analysis of the initial simulation results, make adjustments to the tool paths, the tools, or machining parameters to address any identified issues. This may involve changing the toolpath strategy, altering the cutting depths, adjusting the feed rates, and selecting different cutting tools. And then we have to continue running the simulations again with the adjusted toolpaths and machining parameters analyze the results, focusing on the previously identified issues to determine if the adjustments have resolved the problems, if issues persist, or new ones arise. Further adjustments will be necessary. This iterative cycle involves to continue on making adjustments, running simulations, and analyzing the results until the desired outcomes are achieved. This process may require several iterations to reach an optimized, efficient, and error-free machining plan. And well, as all we can do an iterative process, but in the end we need a final verification and to approve the final model. Once the simulation results met the desired criteria, to perform a final verification and to ensure that all potential issues have been addressed, we may approve and verify that we may include a comprehensive review of the tool paths, the tool selection, the machining parameters, and also the predicted outcomes such as cycle times, surface finish, and tool wear. In the end, we need to make the decision to start the machine and to start cutting. But we need to always simulate and check before the machine process starts. With the final verification complete, the optimized tool paths, the machining parameters can be implemented in the actual machining process. The iterative process of CAM simulation and verification helps to minimize errors, reduce wastes, and improve efficiency. And this will ensure a high quality finished product. On the right side, we can see a picture of the process of verifying and all the iterative process of the quality check for a plastic element. Well, we have to cut the plastic to size, we have to smooth the edges, make the quality check. If it fails, we have to do it again. If it passed, we have to set up in vise, line up the cutting tool, and if it fails, we have to do it again. If it passes, we start the machining. We do a final check, and if it fails, we have to bring it to the recycle bin, or if it passed, we can bring it to the customer. Well, and I already mentioned the different software that you can use, for example, Autodesk Fusion 360, Mastercam. We've seen a video of Siemens NXCAM and VeriCut. There are other CAM softwares that you can use. Here I'm mentioning some of them, each of them with their own benefits and also restrictions. Depending on the machine that you're going to use on your warehouse, you will select the appropriate software that you need. And well, when we integrate BIM and with CAM simulation and verification, we can get valuable information from the simulation and verification, such as the material properties, maybe the geometric complexity, and tolerances. This information will help that the CAM simulation accurately represents the final part and the expected machining process. And while validating the BIM data through CAM simulations, we can allow designers to identify potential issues before the construction begins. This integration helps to streamline the design to manufacturing process and ensures a smooth construction process. Coordination between BIM and CAM models, it's important. Mostly, well, first of all, we need the BIM model as close well, to be the exact same representation from reality. So we can use the CAM model and fabricate. By maintaining coordination between these two models, it's essential to ensure that any design change or update will accurately reflect in both systems. This synchronization will enable the design and manufacturing team to work collaboratively, reducing any errors and improving the overall efficiency of the construction process. What we're seeing here is a cabinet, and well, we already checked the dimensions on the BIM model, and it will adjust to the job site, and it's ready for fabrication. But this coordination is important so we don't have any errors on the real world on the project. Well, also by incorporating assembly and installation constraints from BIM models into CAM simulation, BIM models can provide information on how to construct, assemble, and install these building elements. By considering these constraints during the CAM simulation and verification, potential issues can be identified and resolved before they cause delays, additional costs during construction, and this helps to ensure a smoother construction process and a higher quality final product. Well, the purpose of this presentation was to explain the objective of CAM simulation and verification. This was intended for design engineers, manufacturing engineers, and architects. And this aims to educate the audience on the benefits of CAM simulation and verification in design and the manufacturing process. The benefits of CAM simulation and verification will be to have increased design accuracy and precision. The CAM simulation can help to identify potential issues, and we will have a better precision on the final product. We will have reduced design iterations by catching design issues early in the process. The CAM simulation can reduce the need for multiple design iterations. We can also have improved manufacturability. CAM simulations and verifications can help to ensure that the designs are optimized for the manufacturing process, and this will be reducing the costs and improve the efficiency. And finally, we will improve the collaboration of the team between the design engineers, the manufacturing engineers, architects, and other stakeholders, leading to a better outcome. And well, with the CAM simulation and verification, we can increase the efficiency of the project or the part that we're fabricating. We can have a streamlined design and manufacturing process, efficient cutting and decreased cycle times, and maximized machine uptime. Well, now as a final video, we're going to see how we can simulate a basic simulation with Fusion 360. In this example, we're going to see how the software works and how to simulate a fabrication part.
Hi everyone. Programming a part in any computer-aided manufacturing software can often be a disconnected process between what the toolpath looks like on screen to what really happens when running it on a live machine tool. This difference often means that considerations like machine limits, controller options, and special functions are less likely to be considered when creating toolpaths in CAM software. This often results in programmers and operators adjusting programs on the fly and can cost valuable time and money. Having the ability to simulate toolpaths on a digital twin of your machine aims to address this by allowing a user to gain a more accurate representation of how the programmed part is likely to perform when running it on a live machine tool. In today's video, I'm going to show you how to use the machine simulation by using the built-in Fusion 360 library. Specifying a machine can be done by either creating a new setup or editing an existing one. In this example, I have already pre-programmed a set of toolpaths for this part and want to get a good idea of the machine movements prior to running it on a physical machine. Right-clicking on the setup and clicking Edit will expose the setup dialog. From the machine section within the Setup tab, we can choose the Select button, which will open the machine library dialog. This dialog contains a list of machines which have been utilized in various documents and locations throughout Fusion 360, as well as contains a list of pre-configured machines within an online Fusion 360 library. Clicking the drop-down link exposes the list of simulation-ready files. It's worth noting that this Fusion 360 library contains pre-configured machines and may not match the exact kinematics of the machine you have. Where a more accurate simulation is required, you will need to modify an existing machine or create a new machine to get a more accurate representation. Remember that even though the post-processor uses the kinematics defined here to give a more accurate simulation result, it's always important to make sure your NC output code is correct before running it on any machine. In this instance, the machine I want to use is a HAS machine with a bolt-on trunnion. It's located within the HAS directory. Note here that an accompanying view cube icon denotes that a machine file is simulation ready. Simulation ready machines have fully defined solid model kinematics alongside a linked machine simulation ready post-processor. Once in the HAS folder, clicking the machine simulation filter will display all the simulation ready machines available. You can also view the full list by choosing the top-level Fusion 360 library. Clicking on the machine file and clicking the Select button will begin downloading the machine, allowing the machine file to be saved to a location of your choice. In this instance, I'm downloading it locally into the project folder. Once downloaded, the machine is automatically selected and the Part Positioning tab will now become available. Clicking the Part Positioning tab defines the location of the part attachment, alongside where that part attachment connects to the table. Further offsets can be applied to fine-tune the location required. Now that we have imported the machine and positioned the part, it's time to simulate. Machine simulation is available when simulating from both setup level as well as from the individual toolpath. Right-clicking on my setup and selecting Simulate, we can now begin to see the simulation motions on the machine. I can also see, however, some collisions denoted by red markings in the timeline. This appears to be because the tool I've selected is too short. I can use the new Change Tool functionality to quickly update the tool to a longer tool without needing to recalculate the toolpath. I'll now simulate the toolpath to make sure I'm happy with how the toolpaths are being simulated. To build your own simulation-ready machine, click on the link in the description below to watch the video on how to use the machine builder. Lastly, if you haven't already done so, click the subscribe button and hit that like button. From me, cheers.
Well, and in conclusion, we can see if you have any questions and answers, please let me know to clarify any doubts. Well, this was intended for engineers, architects, and the topic was about simulation verification. And well, we'll be closing here. Thank you very much for your attention and interest that you're interested on the benefits of CAN simulation and verification in the design and manufacturing process. That will be all for my part, and see you on the next video.